very much. So welcome everybody to this new ContinualAI seminar session. And today we have the pleasure to host Martin Mundt from TU Darmstadt in Germany. And Martin is going to present his recent iClear paper. So congrats, Martin and the team, titled CLEVA-Compass, a continual learning evaluation assessment compass to promote research transparency and comparability. This paper is a joint work with Stephen Lang, Quentin Delfosse, and Christian Kersting. And Christian, I would say, is also from Hessian AI, if I'm not wrong. So congrats again, Martin, for this great work. I'm really looking forward to hear your talk. And I guess you can start whenever you want. The stage is yours.
Yep. Thanks for the lovely introduction. So I no longer have to thank my collaborators because you just introduced them. But yeah, it's been a pleasure and I'm really excited to present this work here. So let's dig right into it. Right, I'm going to start with a very simple slide on the motivation behind continual learning. For a lot of you who are familiar with continual learning, it may sound maybe a little bit boring, but there's a reason why I'm starting with such a high level. And so if you think of how a lot of people do machine learning, you often see a couple of steps in sequence that are advocated to be necessary. And it's really a sequence that starts with something like we define an objective. And then if we figure out that we want to solve a problem with machine learning, we collect some data. We maybe prepare this data, clean it and pre-process it, eventually come down to the question of selecting a suitable algorithm, training a model, which nowadays, I guess, a lot of deep learning models are being used, and then doing some sort of testing of the model and eventually integrating it. So usually the motivation behind continual learning is in a very abstract way to not do this as a sequence, but rather do it as a loop. And one of the most prominent sort of things that people consider in continual learning is this question of catastrophic forgetting. So when people ask themselves, what is the state of the art in continual learning, it very often boils down to this question of what is catastrophic, what is the method that alleviates, that prevents catastrophic forgetting the most. So as a short explanation, catastrophic forgetting is really this phenomenon that when you have some sort of model and you train it on some task, which here is illustrated on this visual task, you have a loss that that drops over the course of training. And when you then proceed to move on to some other task that is distinct, and you assume that you don't have any more access to the prior data, so to your prior task data, then you may now make the loss decrease for the new task, but the old loss is going to increase again. So you're catastrophically going to forget whatever you've already observed. And so this is usually what you'll see in, I'll say, the majority of continual learning papers. And quite importantly, however, it's maybe a very vague description, as you may see already. And so, for example, you may ask yourself now, what is the task? What assumptions about sort of the data are valid? How do you even interpret the results? Because people might have different configurations. And I think, James, you should mute yourself. Sorry. And so how do you interpret the results? And maybe also how do you reproduce them? And so one of the key things that you may already get from these questions is that catastrophic forgetting is naturally not the only important element in here. And so we're not the first ones to say this by far, actually. There's been plenty of papers that have kind of tried to illustrate that continual learning is way more than just catastrophic forgetting. There's been a plethora of critiques, in fact. And so, for example, this paper on the top left has done something like a large number of visual classification data sets study where they say our results clearly indicate that there's no model that avoids catastrophic forgetting for all investigated data sets under application conditions. There's been these other works that have said that sure, there are other metrics like accuracy of performance or performance over time, but also backward and forward knowledge transfer. And so how much do you accelerate your new learning? There's memory overheads to consider, maybe computational efficiency. And there's been yet other works on the bottom left here that have said that there may be different fundamental desiderata for evaluation that people consider, and they should be sort of agnostic in a sense. and that there are a bunch of prevalent shortcomings. And while this may sound like it's a huge issue for the continual learning community, just to make sure that it's not a misleading message, it's something that's not really that specific to continual learning. So for example, there's been this very prominent work on deep reinforcement learning that matters, where they've also said that we find that both intrinsic, e.g. random seeds, environment properties, and extrinsic sources, hyperparameter code bases of non-determinism can contribute to difficulties in reproducing baseline algorithms. So there's really sort of this challenge in our community, I believe, in how to reproduce results, but also how to interpret them, and then obviously how to compare them. And so there's been this very sort of big paper on natural science in general that has pointed out some factors that go into this. Some may call it crisis of irreproducible research. And as you can see here, there's some people who advocate that there's multiple factors that go into this, right? And it's not just about the way that you maybe report, it's also about maybe you don't have enough statistical power, maybe your method or code is unavailable, maybe there's a little bit of an incentive mismatch, poor peer review. So there's a variety of factors that can play into these things, right? But in essence, the question is you see a continual learning paper and you see a table and some performance results, and you kind of ask yourself, is this the state of the art of continual learning now? And now there's the way we've just said that you could critique this and maybe try to formalize desiderata, but there's also another way to approach this, which is where we have drawn our inspiration from in this paper. And that's this path of basically drawing inspiration from promoting transparency, really. And so two of the really most prominent works that have recently gone down a similar path are these work of dataset sheets and model cards. So what they do in a sense is they say that it's okay, it's perfectly valid that there are multiple models, there are multiple data sets, people consider them in different use cases and scenarios, but somehow we need a way to make clear what's been done and what the motivation and intent behind it was. So model cards try to make this explicit in such a report sheet here, where you mention your intended use, the factors you consider in your data set, the metrics you report, but of course, kind of limited to this like static view of machine learning and this like train once, evaluate once. Dataset sheets do something similar, in fact, for dataset composition, like how it was composed, what are the, so is it coherent, is it compliant with ethical guidelines, and so on. And we really wanted to go down a similar path for continual learning and in a sense, lay open the challenges with respect to setup and evaluation of continual learning. So in that sense, we then proposed the Continual Learning Evaluation Assessment Compass, or CLEVA-Compass for short. Now, how did we derive the CLEVA-Compass in detail? What we've really done is we've started from basically the beginning of asking ourselves, what is the static machine learning workflow that people consider, and what are the questions involved in such a static machine learning workflow? So it's a little bit similar to the diagram you've seen on the first slide, but already drawn in a circle because we're going to extend it to the continual fashion on the next slide. And as you see, each of these sort of steps here has a box on the outside with a bunch of sort of key points that are questions that you may want to consider when you design your entire machine learning system, right? And as we can see here, it's not just the question of, do you pick a certain inductive bias, a certain architecture, certain functions in your model, and a certain loss function, but it's also really these questions on what is appropriate data to train and evaluate on, how much redundancy versus diversity is in this data set, do you need to clean and pre-process it, what does your test set evaluation look like, are there any failure modes, maybe you need to consider the questions on robustness, but also like how to save the model, how to version it, and so on. And so then we've asked ourselves, because many of these questions are kind of tackled in isolation, so a lot of the literature will pick one of these boxes and go into a lot of detail on them. What changes when we go to continual learning? And the main message here is that these steps essentially become intertwined because they can no longer be separated so easily. And in a sense, when you now ask yourselves about data amount and redundancy versus diversity, for example, the changes to, or in addition, there come these factors on in every step of your loop. What data do you really select next? How does the order of the data maybe affect your results, your training? How similar are these tasks, the data that you feed in? Is there maybe noise in the stream? Are there distribution shifts? And then triggered by these questions. Is the model you're using still okay? Does your architecture maybe need to be extended? Do you need a new inductive bias? Does it forget in training? Do you need to prevent this? Maybe your updates could be selective. Maybe they could be online if you care about computational efficiency. And it goes around the cycle. So there are a lot of additional questions, and it's not very simple to separate them, right? This also for prediction, we now need to ask ourselves, like, what are evolving test sets? What does it mean? What if maybe you put this out in practice like a robot? Can you even define a test set in a sense, or are there unknown factors that will appear that you cannot account for upfront, right? So we're using this as an inspiration to kind of first illustrate how difficult it is to think of continual learning and really boiling it down to this like single definition, because there really is not this like single agreed upon formal definition of what constitutes continual learning. Now, interestingly, of course, we're by far not the first people to consider something like this. And what I'd like to illustrate on this slide is that we've done a diagram here where you see the number of publications versus the year, and you see that they go up in different, let's say, paradigms of machine learning, such as like transfer learning, continual learning, but also few-shot learning, and so on. And arguably, if we take a deeper look at all of these individual paradigms, we'll see that each of them, in a sense, has a continuous element already. So continual learning, in that sense, as the word we use, is really not the only thing that that cares about things that evolve over time, right? And quite interestingly, maybe on the right side, we can also see that there's been a little bit of a shift, maybe from the use of the word lifelong learning and continual learning over time. So in the last 3 years, the use of continual learning has increased quite a lot. I'm not even perfectly sure if there is 100% difference between continual and lifelong learning. Maybe it is very nuanced, but I would consider these to be even synonymous. So what we argue is that basically this is the source, or this is one of the sources, why continual learning evaluation and reproducibility and comparability becomes so convoluted, because there are so many paradigms from which you can now draw inspiration in your setups and in your evaluation, depending on what you care about. That is just not so easy. And so we try to map this out in the paper as I said, as the pre-step to the CLEVA-Compass derivation. And I'm not going to walk through this diagram in excessive detail now, because it's A, possibly quite small on the slide, but B, it's also quite large. But what you really see in this diagram is there are these machine learning paradigms now listed in these boxes, and each of them have a paper that has provided a definition, a very prominent paper, in fact, that has provided a definition for this. We went down this route because we wanted to avoid sort of pulling in our own definition here to twist it in a way that fits into our view, right? So we've picked prominent papers that have provided definitions. And then what we've really tried on these arrows is we've tried to put the relationship, or like the crucial differences, what happens when you move from one paradigm to another. And I'm going to just illustrate this to you on 2 examples here in large, so that it's easier to see. Starting off with transfer learning, because I think transfer learning is possibly the thing that most people are familiar with, and it's also maybe the easiest to explain. And so if you look at the definition of transfer learning of Pan and Yang in 2010, they essentially say that a domain D consists of 2 components, which is a feature space and a marginal distribution. And then given a source domain and a learning task, a target domain and a learning task, so with the source and the target in the index, transfer learning aims to help improve learning of the target predictive function. That's really the essence. And then there's nuances like usually the domains are taken to be different, but maybe the targets can be the same or cannot be the same. If they are the same, some people would maybe call it domain adaptation. But that's basically the thing. You're trying to train on one data set and then train on another data set, and using whatever you've extracted from the source, you want to help improve the target. And so if we take a look at this, I think this is where many continual learning approaches draw their inspiration from quite obviously, because the main difference could perhaps be boiled down to the fact that in transfer learning, we primarily care about optimizing this target predictive function. But in continual learning, we would also additionally like to avoid forgetting of the source. So if you think about the difference here, there could be a lot of commonality, for example, in learning classes incrementally, but just the sort of the objective is slightly different with a slight twist, and everything else maybe stays the same. So I think this is, or maybe as a hypothesis, this is where the catastrophic forgetting focus comes from a little bit. But just for illustration, there are other paradigms, like I said before, that have maybe an equally interesting continual component. And just to pick an example, then here again, active learning and open world learning are pretty interesting. So in active learning, reading out this definition again, the key hypothesis is that if a learning algorithm is allowed to choose the data from which it learns, so in order to be curious, it will perform better with less training. So basically you iterate through time, and instead of presenting a fixed data set to the learner, you let the learner choose what data to include next by itself. And if you want to extend this to open world learning, then in addition, you maybe now also consider the fact that not all data that you see in the future is known. So there may be some completely unknown concepts that even you yourself don't know that you first need to identify before you can maybe label them and include them in some updates. And so arguably, this is also continual learning in some way, or at least let's say you could include it quite easily into a continual learning setup because it already has this idea of data arrives over time. And why is this maybe just as important as catastrophic forgetting? And I usually pick this example to showcase this, following on this active/open world learning idea. It's this thread of unknown unknowns. So for instance, if you train a neural network on fashion images, like the fashion MNIST data set, and so you learn to classify these fashion images, and later maybe you put in an input from an animal picture, like from CIFAR or ImageNet or whatever, you'll quite obviously get a classification that's going to tell you that some animal is a t-shirt. This is not very surprising in the sense of that that's the only thing your classifier has learned. Mostly like softmax classifiers are forced to give you an output. But maybe the interesting part here is that if you plot something like the classifier's confidence, so the sort of the chance it predicts that something belongs to a class, versus the amount of images in a data set, here you'll see that for the green data set, the fashion and the strained one, it's pretty close to 1. So it's 100% confident that this class is correct. But for all of the other unseen data sets, it does basically the same. So it's very overconfident. So it's making a mistake, but it's very hard for you to identify that it's making a mistake as sort of as a model, as a non-human. And this is an age-old sort of problem, which if you think about continual learning, where you now maybe don't want to put a predefined sequence, like say you train on one data set until convergence, and then you pipe in another data set as a human until convergence. So if you as a human don't control this, but just expose your continual learner to a data stream, this problem or this challenge may become increasingly relevant in addition to the catastrophic forgetting. Now, I've talked a lot about setup, right? And again, I think I want to now emphasize that the main gist of the paper now and our primary proposition is not that there's a certain way to think about the continual learning problem and that this certain way is correct or incorrect. I really think, I mean, I've spent a couple of years on this problem now, and in the beginning, I thought it would be nice to come up with a definition. But now I really think that the more distinct applications there are, and there are numerous ones, the more sort of valid existing continual learning scenarios there are as well. Because not every one of these aspects is interesting for every single application. But what is really important, I think, is that we start to make this inspiration and setup transparent, and then also, in that sense, promote the comparability. Because when we just sort of pick similar data sets and report like only catastrophic forgetting value, all of these, like let's say, intricate nuances and inspirational detail, it drowns, and it's no longer clear how to interpret a value. So that's why we propose the CLEVA-Compass, and the CLEVA-Compass is really, in essence, a visually compact form of everything I've just presented on the previous slides. So I've blurred out part of the CLEVA-Compass here because I want to walk through it with you step by step. And in the center of the CLEVA-Compass, that's why it's called a compass in a sense. It's a star plot, it's a radar plot that has different paradigms on the radar. So you may have, for example, this open world idea on this CLEVA-Compass here, or the idea that is online, maybe it's also federated and so on. So in a sense, the star plot allows you to indicate for a specific method whether or not a specific paradigm has been used for inspiration, and in a sense, whether the setup kind of conforms to that idea. And so in this diagram here, we've just taken 5 methods from the literature to kind of plot them into this compass. And you may already see that they're really distinct, which is, I think, part of the point we want to make. I will note that we have obviously picked these methods such that they are distinct. So there are, of course, methods that are really much closer to another. But I think the important element to highlight here is that all 5 of these methods that we picked actually report on the same image classification data sets. So again, if you were to now see just the table of a catastrophic forgetting accuracy number, maybe they're close to each other, maybe they're not. But most importantly, what does it actually mean? Because it's quite hard to compare something that's maybe federated to something that's online, something that has this open world idea where there's unknown data instances involved. Maybe this one sort of method gives you uncertainty estimates, which can be really valuable, right? So it's kind of hard to, again, boil this down to a catastrophic forgetting value. Now, you will notice that on this radar plot here, there are, it's not just a single point that we indicate, it's actually a choice of 3 points. So quite trivially, maybe if we have a point in the center on one of these axes here, it just means that this is not taken into account. But then there are actually a distinction between sort of this inner ring and this outer ring. And what these rings do is they indicate the level of supervision in a method. And now this may be a little bit unintuitive at first, because initially you might think that, oh, well, if I do an image classification task, then my method is obviously supervised. But quite interestingly, the method may have a supervised objective, but not every one of these sort of paradigm inspirations needs to then also be supervised necessarily because of that. And I think just to give you a very easy example, it's this idea of episodic memory. So in episodic memory, we want to avoid catastrophic forgetting with this idea that we retain like a small subset of our original data set and just keep it in a small memory buffer. And so if we continue training on this and these instances are representative of the entire data set, we can avoid catastrophic forgetting. But now there's obviously a question of how do we pick these instances? And so one very prominent way to do this is the supervised way here would be to, for example, have a classifier calculate the mean of this classifier across all dataset instances of this class, and then calculate for a dataset point how close you are to this mean. So this involves supervision, not only in the objective of classification, but also in the way how you select these subsets of data. But you could also go, in a sense, and be more agnostic, so that even if your objective is image classification, your way of how to avoid catastrophic forgetting is kind of agnostic to where you put it in. So for example, the green method here has actually just used a way to uniformly fill a memory buffer from the data set. So you just pick instances at random because they say at a specific size, that's good enough. And the advantage of that would be that even then, if you move to non-classification tasks, you could still use this method. So in that sense, we believe it's important to distinguish this level of supervision really for every access, in addition to just saying that your overall objective now may be supervised or not. So we understand that maybe makes this a little bit more complicated, but I think this is really important to sort of also showcase a little bit of the generality of the mechanisms we put in, because arguably most unsupervised mechanisms will easily adapt to a supervised version, but not the other way around. And right. So finally, this was a lot of inspiration and a lot of on the setup, but there's also this question of how do we report? And so how do we report really then comes back to these practical measures that we want to put in our paper. I think we still all agree that it's really nice to put inspiration on our paper and explain setups, but at some point we do actually want to compare. So if we figure out that we do want to compare our methods, then of course this inner sort of star plot can indicate how reasonable it is to compare. But we've also now included this outer compass level which really just lists a couple of metrics that people have proposed in the literature over the years. So just to clarify, none of these metrics are proposed by us. To just sort of indicate, if I wanted to do a fair comparison now, what should I be reporting, or maybe what are things that other people are reporting that I'm missing, or where other people place their focus. So we can see, for example, that maybe the green and pink method here, they care about forgetting, so they actively measure forgetting, but maybe the purple method here cares a lot about compute time and parameters in addition or instead. So again, if we think of just making this maybe easy, going to this easy pitfall of just looking at a forgetting number, we would then need to take into account maybe that compute time and parameters can induce like really drastic trade-offs. So in that sense, as a summary of this CLEVA-Compass, we hope that this allows people to, first of all, summarize their incentives, so make the incentives clear. We hope that it then encourages the transparency. And because of the way that the metrics are listed, the comparability really is increased. So on the one hand, we get an indicator of how reasonable it is to compare, maybe what steps we would need to take if we wanted to do a fair comparison, but also it kind of tells us what specific focus a work takes. So if we're a practitioner, we can identify works that kind of fit our needs. If we're a researcher, we can identify the works or justify the works that we want to compare to and make clear why this is reasonable. So I'm intentionally going to keep this a little bit short here and not go into like a long list of examples. I do want to point out, however, that in the paper, there is a table for all of these measures where we sort of explain what the measure is and who has proposed it, like why it matters. We have also included like mathematical definitions that exist in an appendix. And for the star plot on this level of supervision versus unsupervised, we have included examples for each and every axis in the appendix as well, so that people may get an intuition of what this actually means in case they have not encountered it before. And then I also want to stress, because I hope I've made it clear in the beginning, but I would like to stress that although I think the CLEVA-Compass is nice, it does not replace things like dataset sheets or model cards. It's more like a complementary thing. So if you think, for example, about these popular reproducibility checklists at NeurIPS and other conferences, the CLEVA-Compass sort of doesn't exempt us from following like the general scientific rigorous practices, like including the code or reporting standard deviation error bars across our experiments. We should obviously still do all of this instead. So in case it's not been clear, I want to just clarify that this is in addition. And so on the last slide, I think I'm going to end on this a bit of a like call for action. Out of the review process, we've gotten this really nice feedback of why don't you come up with a GUI, a graphical user interface for the CLEVA-Compass, so people have it easy to not only reproduce the CLEVA-Compass, but also like put in their own methods. So that's exactly what we've done. So we created this CLEVA-Compass GUI, which has all the elements listed here on inner level, outer level. You can pick colors for methods. You can name your method. Each of the elements has a little sort of toolbox. When you hover over it, like here it says for backward transfer, it's going to give you like a short explanation of what that means, so you don't have to like flip back and forth to the paper all the time. So we hope this is a way that sort of helps the community. And what we've done is we've put this into the repository here, but also in this repository, we've started putting in the 5 methods in the paper, and you can load those with the CLEVA-Compass here on the download methods button, so that you can easily sort of plug them in addition to your own method to facilitate these comparisons. And for the call for action, in a sense, is that we would really love to kind of extend this to somewhat of a comprehensive database, so that everyone can sort of like start contributing their own method, maybe put in an old method also, so that the longer we go in time, the easier it gets to really compare our landscape. Right, and then naturally you can, once you've created the CLEVA-Compass, you can export this to an image or actually LaTeX code. So we've this is all coded in LaTeX, so you could just like easily copy paste this into your paper and it gets rendered. And with this, I think for now, I would just transition to questions, and maybe we can just have a little bit of an interactive discussion instead of me talking even more.
Great, very nice, Martin. Thank you very much for this. So yes, I guess that from now on, people feel free to write messages here. Just open your microphone, speak, leave comments on YouTube. As you can see, we have plenty of ways to interact with Martin. And just to give people the time to think about some question, maybe I can start. Well, first, I just wanted to say that I really like the paper, but in particular, I really like the appendix of the paper, right? So, I mean, I'm not saying that the main text was not good, but yeah, the appendix was really nice with all these. Also, like the description of the metrics and so on and so forth. It's something which you can really read and just relax and go with the flow and trying to really focus on each element of the CLEVA-Compass. And I think it's really a good reference if you just want to know which are the metrics, what they are computing, and so on and so forth. So this review work, let's say, is really appreciated, at least from my side.
Thank you.
And in terms of ContinualAI, I also think that this paper represents one of the efforts that, as a community, we are trying to pursue, and one of the objectives actually of ContinualAI. So the meta research problem. So not only focusing on research and solving a specific challenge, maybe with a new strategy or something, which is definitely important, but also to understand and trying to reason on the research trends and go on a higher level, like on a meta level, if you want. And so, I mean, I think this paper is really perfect for a seminar of the ContinualAI Association. But I mean, apart from the compliments, which that
now comes the hard part.
They're not enough. So I just wanted to point out something which is not an issue per se, but it may become one important point for the CLEVA-Compass. So the problem of let's say, common nomenclature and taxonomy. So having this set of common definitions, like the metrics or the scenarios, is really important, right? So if you don't have a common understanding of what something means, it's really hard to make these tools to be used by the community, because no one knows exactly what they mean, and so on and so forth. So do you think that this CLEVA-Compass is going to be extended in the future because for example, new metrics will come? Or for the moment, do you see it as a stable, let's say, first result on which others then can refer to? Because to me, the categorization is always, and the taxonomy is always difficult to stabilize. It's always something that moves along the way, and so it's also hard to keep up with it. So I don't know if you have any thoughts really about this.
It's actually yeah, it's something we've thought about a lot, and it's actually something that has come up on the iClear review process, which I guess you can see on Open Review if you're curious about it. So there's a discussion on it there, because there's been sort of not really, like you said, it's not really an issue, right? It's more like a question without an answer. And I think there are various elements to it. So the first one is, I think, if we become too rigorous, like too sort of mathematical in our definitions, it's, on the one hand, it's kind of nice, right? Because we get like this formal tool, but on the other hand, we also constrain ourselves too much. So this is why the definitions I've read out earlier, which we've taken from the literature, they have a mathematical component, but there's like a little bit of ambiguity left to it, right? So like you said, that people may still lay this out like slightly differently. And so that may indeed happen. At the same time, I don't really think this is a problem, and I'm going to get to the extension part in a second, but at the same time, I don't think this is a problem, because I mean, the interesting part about the CLEVA-Compass is that it's not one of those things where essentially, like, if you maximize it, you're the best, right? So in the sense, like, if you just fill out the entire circle, that doesn't mean you're the coolest method. It just means that you're like caring about certain things. In fact, like some of these elements on here, like an episodic memory, a lot of people will consider this to be a drawback instead of an advantage, right? They'll say like, I don't want an episodic memory, taking more memory is bad, so I want to be in the center. So in that sense, maybe if you lay this out like slightly differently, it doesn't hurt you, right? Because you can't just take a look at it and easily say this one's better than the other. It's more like a preference thing and fair comparison thing. And I do hope that, let's say, with the definitions we put in the paper and the explanation of the metrics, most of it is going to be sort of comparable to the degree that it benefits the community. Now, the extendability part is it's quite interesting because there's this little bit of a challenge in there. So we initially thought that we just open this up as a repository for people to kind of extend it, right? But then we realized that if we do that, that kind of means that we're putting ourselves into this insane position of power that, quite honestly, I do not want to be, right? I don't want to be in this position where I have like access, like I have control over the CLEVA-Compass. Someone does a pull request, and I now decide whether this needs to be included into the CLEVA-Compass or not, because then I'm biasing this quite a lot. So in that sense, I do believe that the current version is kind of stable in the sense of that I think the releases should be not really rolling, but a little bit discrete. So I don't think like every new metric that pipes into a paper should immediately also go into the CLEVA-Compass, because there's also like this kind of threshold of kind of like of mass, right? Like if you think, for example, about the federated idea here, I think there's like a 4-year difference between the first federated learning papers and the first like continual federated learning papers, because it's always like takes some time for things to get a little bit adopted. So I really think that there should be like these discrete versions of the CLEVA-Compass, and I don't even think that we should be doing this, like we as the authors should be necessarily doing this discrete versions. Of course, I'm very happy to be involved, but I really encourage the community to kind of take a charge here as well. And I mean, yeah, like think of some things like maybe causal models, right? Like if some people now start doing causal models or things like that, it's not really easy to fit it in here. And so in that sense, surely at some point this will have to develop. I think for now we've hopefully done a good job at covering as much of the landscape as is reasonable right now. So like you said, a large portion of our paper is in fact a survey in that sense. And yeah, I think then the rest can kind of, I mean, as soon as we start aggregating metrics, as soon as we start aggregating methods in the repository also, at some point we're going to see that maybe there's a necessity for a version 2.0.
Yeah. No, I agree with your view in which, I mean, yes, if you have complete control over the CLEVA-Compass, you may risk, as you said, to bias the developments, maybe even to slow developments down in the field. On the other hand, if you allow for, I mean, if this CLEVA-Compass becomes very popular and each and every one of us has its own version, we might need like maybe I clear 2025 CLEVA-Compass. So a compass of, but let's not get away with this. But yeah, I think that's in the end it's up to the community, right, to find the good trade-off. So it's likely that if we have like an official CLEVA or a tool out there, yeah, there might be some additional extension with one new metric or something, but in the end, people will tend to reuse what's already there. At least science tends to this direction.
I hope this just goes similar in a way to like the datasets sheets paper, right? Like dataset sheets were also in development, and then they were quite actively used, for example, in Europe's dataset and benchmarks track. And it seems to fit like most use cases initially, but eventually also there it will evolve. And so I'm hoping we can go with this same approach. And there's like a static sort of version for a period of time before it evolves into another one.
Yeah. So another question I have is if you have plans to keep track, for example, of the different branches that may emerge from this first tool. And if you want to extend the tool yourself, maybe to different areas, I don't know, like reinforcement learning compass, or if you, plan to use this approach in other fields.
Right. So I think the aggregation of methods part is one part where we'll hopefully then see, maybe also in raised issues in the repository, that there are some things that are not covered. So in a sense, I hope we can keep track through that. About the reinforcement thing, so we have, let's say, taken some care in making sure that this current illustration is not specific to anything really in particular. So that's why we also cared about this like supervised versus unsupervised thing. Now, of course, reinforcement is a little kind of fits somewhere in between. One of the co-authors of this paper, Quentin, is actually actively involved in reinforcement learning publications. So we also try to see a little bit that we don't completely discard something. I hope for now that for the works that I'm aware of, or that we're aware of, it still fits. But yeah, at some point, again, like I said before, we'll need to maybe extend it. For now, I hope that we have a good amount of supervised, unsupervised, and reinforced scenarios covered. And I hope that sort of if the number of things that are not covered so far, that they're kind of small enough that they can maybe just be mentioned for now in an additional comment in the figure caption or something, so that it becomes clear that there's maybe one more difference. But I hope that we did a good enough job so that there isn't suddenly a method that now just doesn't fit anywhere and it has 17 different aspects. And
yeah, makes sense. So I see that we have a question from the YouTube. So Traki Garg, sorry if I mispronounce the name, as I'm sure I'm doing, but asks, does the paper also specify comparison metrics that could help us understand relations between different learning paradigms? So as a follow-up, everyone creates their own task and learning paradigm, and these are largely non-comparable. So is CLEVA also providing a way not only to see if these two approaches are very distinct between each other, but also providing some metrics to nonetheless try to compare these two approaches?
Okay, so we're not immediately proposing metrics in a sense of if you want the difference between that and that, you have to evaluate this specific mathematical term that's going to tell you the difference. I think that would be extremely nice, but maybe even more challenging than what we've did so far already. It would certainly be a very large effort that I'm sure a lot of the community, in general, the machine learning community, not just the continual learning community, would appreciate. So if you have ideas for that, I strongly suggest you to go for it. What we have done, however, is this part here, right? It's not a metric, right? But it's kind of, I guess you could derive a metric from it, of course, with a little bit of ambiguity. So like I mentioned with the transfer learning example, right? It kind of, in a sense, for example, the forgetting part is the difference between these two paradigms, right? And then the few shot learning to transfer learning part, the number of instances part is the difference here. So what we've done is in this table 1, where we have the measure, we can at least try to indicate sort of which aspect this measure addresses, right? So for example, for data per task, we say that the number of data instances would be a primary indicator for sample efficiency and would provide the context, for example, for few shot settings, right? If you indicate that this is very low, then I guess people would consider the few shot setting, because the main thing about few shot setting is having few instances. So in that sense, we have these indicators, and there's these mathematical definitions of many metrics in the appendix, but we haven't really made the differences explicit mathematically. I'm not even sure if it's possible for some of these. I mean, for some it's easy, like the transfer thing and the forgetting part, or the data part and the few shot part. For others, it may be a little bit more complicated. Please let me know if that answers your question. And I am aware that I think there's a 30-second delay on YouTube in the stream. Yeah, so we'll see in a second.
Yeah, I'll fill this this void by saying that yeah, it's definitely an ambitious objective, right? It will be like there's something, the concept of reducing a task to another, also in the, let's say, in computer science theoretical part. So if we manage to find a task to which we can let's say reconduct all the others, it's going to be easier, but it's definitely something that it's ambitious.
Yeah, I mean, at some point we may also just want to acknowledge that some things maybe are not immediately comparable, right? Like, I mean, desire for comparison is always nice, but maybe sometimes we should not compare specific things. Like sure, there are a lot of, you could say that there are a lot of buzzwords, right? Like there's a buzzword for machine learning paradigm and people have created this, but there also very arguably is a reason why they exist. So there was a reason why it emerged and why people wanted to make this distinction. So maybe sometimes not relating everything to everything sort of very explicitly in a mapping is also okay. And we can keep it a little bit at this sort of non-mathematical level and just accept that we don't we can't exactly do this mapping, right?
Yeah. Anyway, your question was right on point, so I think that clarifies your answer. Sorry, was right on point, so I think it clarifies the question. She's also saying, I think the paper towards a theory of out of distribution learning does something like that. So the CLEVA-Compass, along with the theory defined in that paper, would be of great use. I don't know if you were aware of this paper or not.
Yeah, so we are aware of like out of distribution detection, recognition, whatever papers. I think there are a lot of sort of next steps that we should now take. I think the mentioned one is one very particularly good idea to delve into this. Absolutely. I mean, the next step obviously now that we sort of start mapping this out, it's also sort of, let's say, exploring these directions further, right? I mean, we could now see that there are certain aspects maybe that are less explored than others. So arguably, for example, the exemplar rehearsal, this memory buffer idea has been explored quite excessively in class incremental learning, whereas maybe these outer distribution questions and distribution shift questions they are partially addressed, but are far less prominent so far, right? So there are certain areas that maybe are more interesting right now to explore than others, without me trying to tell anyone sort of which area is more interesting.
Yep. So any other questions from the audience?
I have a question.
Yeah, go ahead.
So you mentioned in the inner level that it's supervised and unsupervised. So what about people are using training in a semi-supervised or self-supervised manner? Like how can they use this compass?
So okay, I think that's a really interesting point. In my opinion, self-supervised, I mean, it sounds like supervised, but what we refer to as supervised here is really this idea that there's a label that comes from a human. So there's a necessity for a human to label things, because sure, self-supervision, you can call it supervised because the objective has this explicit comparison, but say it's not really clear like why this is not unsupervised, right? So for example, if you think of something that people do in self-supervised learning where there's maybe a permutation and you want to like recover this permutation and your objective, then this is not really necessarily that different from what an autoencoder does when you do a denoising autoencoder. In a sense, somehow that's also self-supervised, unless I'm completely mistaken, right? I'm not really sure if that requires a separate sort of categorization and why it wouldn't fit into unsupervised learning in that sense. Because it doesn't have this component of humans need to label things. But of course, that's kind of a nuance on definition of these terms, right? I think for the compass, the distinction or the important distinction is that so do you require kind of these human labels, right? Like, do you require these labels and or not? And in that sense, I would argue self-supervision does not require these labels. But feel free to correct me. Self-supervised thing is an emergent self-supervised supervision is an emergent topic. So arguably, maybe CLEVA-Compass 2.0 will need to include self-supervision. I don't know.
But isn't semi-supervised is kind of in between? Like you use labels and some of not.
Oh, sorry, did you say semi-supervised or self-supervised?
I mentioned two, like semi-supervised.
Okay. I mean, semi-supervised, again, I would go back to, if you are able to do things unsupervised, then including a supervised signal is usually kind of easy, right? So, for example, if you have an autoencoder that learns the distribution, including a label somewhere into this is not really challenging in that sense.
Would you put it on the compass on supervised? Sorry, on supervised if it was semi-supervised?
I'd put it on the outer circle, but I understand that this may be so that there's a little bit of sort of flexibility in there, right? But I think the main argument is here that you want to demonstrate sort of like what's like the most general thing you could go, and so if you could go unsupervised, but like inclusion of labels just gives you some improvements, then I would still go for the outer level, because like I said, I think any unsupervised method I know, or most of them, including a label is usually quite doable, and that's really not the challenge necessarily.
Then the opposite, I guess, for semi-supervised, you'd be a low number of labeled data, and the idea is that you're adding a bunch of cheap unlabeled data to boost your performance. So I'm curious if there would be a way to, like, obviously we're not changing the compass, but to like think about it that way. To put it halfway on the compass or something.
Put a halfway level in between without changing it. Yeah, I mean that'd be like I think that'd be a minor change that also doesn't really hurt anyone in that sense. Yeah, it doesn't hurt the comparability if you want to, right?
I think there's a lot of nuanced ways you could discuss how it would be, quote, included on the compass. But yeah.
Right. Yeah. So this discretization on the sort of supervised versus unsupervised level. I mean, you could do this more nuanced if you wanted to, I guess. Yeah.
Yeah. I mean, there will always be new terms and new possibilities to expand this kind of tool. I think that in the end it boils down to the amount of let's say of pressure that there is to add something. As soon as one feels that the community is really asking for something because now is needed this distinction, you can add. So it's nice to have these also evidences emerging from the community. That's what's useful.
Right. Yeah, I mean, if like 100 papers emerged on semi-supervised continual learning in the next year, I'm pretty sure we can adapt to CLEVA-Compass. Exactly. So we should, yeah. That's.
Yeah, I agree. Any other questions? Don't think so. But
I have a question.
Oh yeah, feel free. Go ahead.
Thank you very much, Martin, for your presentation. I would like to hear from you how different methods that has very little or no overlap in the CLEVA-Compass be compared. Is it an indication that they should not be directly compared because they use completely different approaches? Or I'd like to hear from you.
Okay. So first of all, I think any comparison that we do in continual learning, we should try to maybe be as broad as possible and get a little bit away from this reporting a single metric, right? So in that sense of anyway, no matter what sort of method you put in there, don't just report like an accuracy value, like report all the other, like a lot of other values on these ring outside here as well, right? That's the first thing, because it's going to relate to sort of what we discuss on the inside. I think a lot of these things, I'd really encourage people to be extremely cautious in the interpretation. So there are two things. There's a difference between comparing methods, which is not a bad idea per se, right? You can always compare methods, it's great. But according to sort of the difference, there's a different level of discussion involved and a different sort of level of insights that you can take away and claims that you can make. So I think the only problem that we really have in the community right now or in machine learning in general, not just continual learning, is this idea of that there's this like single concept of state of the art, and somehow everyone just boils down to this method is more state of the art and this one is less, right? And so I would argue that for a lot of the things, you can compare these, like, right? Say one of your methods has multiple models, the other one has not. You can still compare them, right? That's one difference. And of course, that means that one model has maybe more parameters, but that doesn't mean you shouldn't maybe also be comparing accuracies or not, but you just should make this sort of trade-off explicit in your comparison when you also then report number of parameters that you indicate that maybe the multiple models version, if it just clones a model, has twice the amount of parameters, right? So that people who read it can interpret this correctly, and you can also interpret this correctly. Now, the problem begins when you start sort of omitting certain details, right? However, I do agree maybe that in addition to discussion, some methods, when you sort of want to compare them and then have the discussion, it will be a little bit obvious that the comparison is kind of really hard to make. Like, so for example, this open world examples or online examples are very primary. Like if one method does online learning and just really goes with this brutal assumption of I have a data stream, I just see every instance maximally once. And then you want to compare this to something that doesn't do this and just like iterates 200 epochs to convergence of huge data sets with lots of sampling, then, yeah, I mean, I guess you can put two accuracy numbers in there. But doing this discussion is going to be it's going to make it painfully obvious that this now constitutes kind of such a large difference that drawing any sort of explicit conclusion from this, other that the methods have a very different focus, is not really possible, right? So in the sense, feel free to do the comparisons. I think that's a great idea. But somehow really factor in the way that you discuss the methods and the way that you report results. And I do understand that maybe there's going to be a little bit of a challenge in doing this when you like submit a paper and a reviewer is kind of, this is recorded, right? I'm not going to say this out loud, but we all know what I'm going to say. And when there is a specific focus on, let's say, taking a look at a table and some figures and maybe reading the text in a slightly faster fashion, that this gets lost, right? But then that's the entire purpose of the CLEVA-Compass, right? Because the CLEVA-Compass is going to it's going to be a slap. Here's a figure. It's going to very prominently display that there's this like huge difference now. So that hopefully, even if you do a comparison, it's already from the start going to become quite clear that the result discussion is not as obvious as just comparing two values and saying the one with the larger number is better.
Certainly.
Does that answer the question?
It answered. Thank you very much.
Yeah, along this line, maybe one last note from my side. Do you plan to, push this tool for conferences? I mean, there are any plans to integrate this tool for example, including it in papers if the paper is on one of these topics and so on and so forth? Or for now, it's just, the tool is there. If you want, you can use it, and that's it.
I would love to answer yes to this question, but I'm not sure if I have the means or sort of the ideas of how to enforce that, right? I mean, it's enforcing maybe is also not the best idea. So for now, I guess we want to just encourage people to use it, and then hope that similar to like other replication tools like checklists and so on, that they just get adopted eventually because people see the benefit. I mean, I think checklists were also like the same way, right? Like in the beginning, it was like, yeah, maybe do it, but then people saw like it's actually quite useful, so let's do it, and it's still in a sense optional. I think NeurIPS forces it, but for the remaining conference, it's still optional. But so I'm hoping something similar will happen here, that people just see the benefit. As people included, other people will see the benefit and it gets adopted. Maybe for a workshop and so on, we can also push this a little bit more actively, right? I don't know if it's generally a good idea to force something onto people. let's
No,
hope
no.
that with enough like advertisement and promotion, it kind of just spreads enough by itself. Yeah.
Yeah, let's see how it goes then. Any other questions? Okay.
No.
If not, maybe Martin can like add some final notes if you want.
Right. So now that you've seen the paper and the presentation, and I hope you liked it, and if you have indeed liked it, then there's a small announcement that I'd like to make, and it's that I'm starting a little bit of my own research group here in precisely this direction. So it's going to be like this idea of open world lifelong learning. So exploring these more sort of generic setups on more of these axes of the CLEVA-Compass, trying to like go into different directions here. And so with the generosity of Fashion AI and the Technical University of Darmstadt, I'm now looking for 2 PhD students with an application deadline April 5th, 2022. For those who are seeing this in a recorded version on YouTube, please do not apply after this date. And there are 2 positions for this on these links, or you could feel free to just email me with questions below. Thanks.
Oh, thanks to you, Martin. So I really wish you the best of luck with this new group, and it's always a pleasure to have more and more groups working on these topics. So, I mean, we'll follow your updates along the way, I guess.
Thank you.
So, since we have no more questions, I think we can also close this seminar for today. So thank you everyone for being here with us. Thank you for the very nice questions, and I think we had a great discussion. And next appointment is on March 31st, so in a week on Thursday, and should be always at 5:30 CHEST, so the daylight saving time in Europe. And we will hear from Xinyo and Kao about provable lifelong learning of representations. So until then, stay safe and have a good day. Bye, everyone.